few more chemical aspects, and then of course you have to pick more of that by money. But let's take a look now at water itself. Because water is really a very funky molecule. Let's face it, it's an oddball. It's an unusual molecule, yet obviously it's critically important for life. We often say that, at least life as we know it in this world, is carbon-based life, meaning it's mostly composed of carbon-containing organic molecules in a water solvent. Now, some science fiction films and writers, and some scientists have speculated about the possibility of some kind of life that's not based on carbon or not based on a water solvent on other kinds of worlds. Anybody remember the original Star Trek series? They had the one back in the 60s with Captain Kirk and said, okay, the original series, they ran into a life form that looked like a large moving rock and spewed highly corrosive acid on people it didn't like. And it was based on silicon, because silicon has four electrons in its valence shell, and it can form 4 covalent bonds. So on the other hand, silicon doesn't work quite so well. It doesn't make the same variety of molecules that carbon does, even though it can form 4 covalent bonds like carbon. The other thing is that silicon, once you oxidize it, that silicon to oxygen bond is very strong compared to the carbon to oxygen bond, and the silicon to hydrogen bond is very weak compared to the carbon to hydrogen bond. So if you oxidize silicon, it's basically a one-way ticket. You can't go back. It's almost impossible to do the reverse. There's something, the silicon equivalent of methane, what they call silane, explodes on contact with even trace amounts of oxygen. Even in Jupiter's atmosphere, which has only parts per million oxygen, there's no silane that people look for detectable in that atmosphere. So that silicon might not work too good. Some people speculate about ammonia as a potential solvent. But as we saw here, ammonia is not as polar as water. You'd have a harder time, aside from the fact that you like to live in really cold temperatures, you'd have a much harder time making these cell membrane barriers. They would be leaky because ammonia is not as polar as water. So water, probably of all the molecules in the universe, water is probably about the ideal kind of thing as a solvent for complex biochemistry. So that's why in that whole unmanned Mars program, their motto is follow the water. Look for areas on Mars that showed signs of past water, and if you got the money, land some spacecraft. Now that's exactly what they've been doing for the past several years. Those 2, Spirit and Opportunity rover, and of course now that Curiosity rover. They're looking and landing these things in areas that showed signs of past water, and they've confirmed that on all these spacecraft. But anyway, so what are the properties of water that make it so good for this kind of thing? Okay, well let's take a look at several aspects here. First, water is extremely polar. It's one of those polar small molecules around. I mean, hydrogen fluoride's got it beat, but hydrogen fluoride's also corrosive. Now, if you're a very polar molecule like that, it means you are a terrific solvent for anything else that's polar. So it's an excellent solvent for polar molecules. It's also capable of breaking ionic bonds, so it can dissolve a lot of ionically bonded molecules, our common salts. And we'll see how that happens in just a second. And that's because it is so polar. On the other hand, because it's so polar, it's an absolutely, utterly, horribly abysmal solvent for anything that's hydrophobic. It's as poor a solvent as my handwriting is poor. No, it's even worse than that. Okay, so you can imagine. And that means you can use hydrophobic molecules as water, as shields, as protective barriers between the cell and the outside world, or one compartment of cell and the next. You can make hydrophobic molecules have a nice little hydrophobic environment to do chemical reactions that have to occur in a hydrophobic environment. And if you had something that wasn't anywhere near as polar, you'd have things like leaky membranes. That's what ethanol does if you have too much of it. Your membrane integrity starts getting leaky and things go in and out that they shouldn't, and then you get drunk and then you pass out and then you die. At least if you do too much of it at once. So it's a very terribly poor solvent for hydrophobic molecules. Okay, and that makes it impossible to have some pretty nice watertight barriers, the cell membranes. Okay, now, talking about polarity, we've said several times that water actually breaks ionic bonds. How does it do that? Let's see. Okay, let's take some sodium chloride and throw it into water. Now, it goes into the water. And recall, those water molecules have fairly strong partial charges on them. A negative charge on the oxygen end, a positive charge on the hydrogen end. So what's going to happen? These partial charges are going to love the oppositely charged ions. They're going to clump and cluster around it. So the oxygen, you have multiple water molecules clustering around this sodium ion on one side. And then around the chloride ion, you have the positively charged ends of the hydrogens on the water molecules, like so. Okay, and they're all attracted to these charges. Now these water molecules are effectively pulling at the ions as if they're trying to pull them apart. And if they actually succeed in pulling them apart, what's going to happen is this. Let's separate this chloride from the sodium here. Okay, here's the chloride out here. And here's some of our water molecules. I won't bother putting the charges in on this case. You know they're there. Okay, this is where we pull things apart. Now we can fit additional water molecules in the area in between these ions now that they're separated, so let's do that. Okay, now these ions are completely surrounded by a three-dimensional shell of water molecules. As a matter of fact, we call this a hydration shell. And the attraction between the collective attraction between all those water molecules and the ions is actually greater than the attraction of the ions for each other. So once you get that shell formed, the ions don't come back. They don't stick together again. So salt water is sodium ions, chloride ions, each of those ions surrounded by the little shell of groupy water molecules. Now you continue to do that. You start pouring more and more salt into water, and pretty soon you reach a point. The more salt you pour in water, you pour some salt water, it goes in the solution, right? Pour some more salt, more of it goes in the solution. But you'll finally reach a point where you can add more salt to the water and it doesn't go in a solution. What's going on there? You've reached the solubility limit. For sodium chloride, it's a little over 4 molar. That's about 23 or 20, that's about 25% salt by weight. A little over 4 molar salt can dissolve into water. But beyond that point, once you're saturated, you pour more salt in, it won't go in the solution. How come? Because when you reach that solubility limit, every single water molecule in there is part of somebody's hydration shell. There are no free, unattached water molecules left. It's like a whole bunch of guys going to a sorority party, right? Problem is, you get 50 women, 50 guys, right? And they pair off. Now, the 51st and 52nd, 53rd guys, they come in there and there's no free ladies left. So they walk out in disgust. Okay. All right, but here it's saturated. You use up all the free water molecules and then you reach your solubility limit. Now, depending on the charges and the sizes of the various ions and things like that, that determines how many water molecules surround and form a shell. So different salts have different solubility limits. For instance, sodium chloride's about 4.3, 4.4 molar. Potassium chloride's, I think, a little less than 4 molar. Magnesium chloride, you could go over 5 molar on that, and so on. It differs from salt to salt. And that just depends on the charges and the size of the ions. But you sooner or later reach a point where you can't add any more and get in the solution because there's no more free water molecules left to pull the ions apart. Now, on the other hand, there are some kinds of ionically bonded molecules where the ionic bonds are strong enough that even water can't pull them apart. In other words, the ions are surrounded by water molecules, but they're not powerful enough to pull the ions apart. Calcium fluoride, what we call fluorite, that's a good example. Those ionic bonds are quite strong. You can imagine how electronegative fluorine is. Those ionic bonds are quite strong. You throw it into water, and it sits there steady. It will not dissolve because water cannot pull those ionic bonds apart. Now, on the other hand, if I take salts and throw it into something that's less polar than the water, like ammonia, liquid ammonia, for instance, many cases it simply won't dissolve because the charges on the ammonia molecule are not as strong and they can't pull the ions apart. Other times they might dissolve some of it, but not as much because they have trouble pulling those ions apart. So once again, if you were an ammonia-based life form, one, you'd probably stink really bad and wouldn't be in this room here, and two, you'd like this is too hot for you. But anyway, if you're an ammonia-based life form, you would have a very hard time using ions in your biochemistry because you couldn't pull the salts apart that generate those ions. So that's another thing with water. Water allows you to get solutions of ions into solution, and ions play critical roles in all kinds of things. Without ions, you would not have muscle contraction, you would not have kidney function, your xylem and phloem, if your plant would not work, your central nervous system, nerve transmission would not work. All of those processes are dependent on ions. And that means salts have to dissolve in the water. If they didn't, you wouldn't have those ions around. And all those processes would grind to a halt. So that's a couple other things about water. But that's not all. Because water is so polar, it makes hydrogen bonds with each other. In fact, relatively strong hydrogen bonds as far as hydrogen bonds go. Now, something like ammonia makes hydrogen bonds with each other, but because ammonia is not as polar, the hydrogen bonds are much weaker. Now, what does that imply? Okay, first thing, water has an extraordinarily high freezing and boiling point for such a small molecule. We told you what the boiling point, approximately boiling point of ammonia is about 60 below on the Celsius scale. The boiling point of methane, which doesn't make hydrogen bonds at all, is about 190 below on the Celsius scale. Cryogenic temperatures. Now, why is keeping water liquid at high temperatures important? Think of chemical reactions. What happens to chemical reactions when you heat them up? They go faster. In fact, they usually go faster than what they call the Q10, how much faster they go per 10 degrees Celsius increase. They go up generally by about 2 to 3-fold for each 10 degrees Celsius increase in temperature. And sometimes you get reactions that they won't occur at all until you reach a certain, or an appreciable amount, and then you reach a certain temperature, and then the reaction starts occurring catastrophic. Like case in point, methane, natural gas, methane combines with oxygen to make carbon dioxide and water. Okay, now, if I were to release some methane gas in this room, not much, at room temperature, the methane would slowly react. It would take about 10 years for half that methane to be gone at room temperature. Now, on the other hand, if I heated it up, I reach a point where they would start to react fairly quickly, and I get myself a good explosion. So, if you have a liquid that has a high melting and boiling point, it means chemical reactions are going to occur at a much faster rate than in a colder environment. And when you think that most biochemical processes are multi-step chemical reactions, where one has to be completed before the next one starts, pretty soon, in order to keep a complex thing like a cell going, you have to have those reactions occur relatively quickly. And it helps to be liquid at a high temperature. So that's an important thing, liquid at high temperatures. High melting plus boiling points. That means faster reaction rates. Okay, that's not all though. Now let's take a look at a water molecule. Let's take a look at ice. Here we have some ice. We're making this kind of locked into place network of hydrogen bonded water molecules. Okay, and that's when water freezes to form ice. The hydrogen bonds, once they form, do not break anymore because the molecules aren't moving fast enough to break them. So we get this three-dimensional lattice work that we call ice. It's a solid. Now, when you start adding heat to the ice, the first thing that's going to happen is the molecules are going to start jiggling around, but they're still chained together by hydrogen bonds. It actually takes a lot of energy to break the hydrogen bonds enough so that these water molecules pop out on their own. In other words, converting ice to a liquid state. And that's because it takes a lot of energy to start breaking enough of the hydrogen bonds that the water molecules are no longer in this frozen lattice, but start moving around. And that's what we call the heat of fusion. It takes more energy to take a block of ice at 0 Celsius and turn it into liquid, into ice water at 0 Celsius, than it takes to take that water at 0 Celsius and bring it up to the boiling point. It takes a great deal of energy. The second thing, what we call the heat of vaporization, here again, you're breaking those hydrogen bonds so much that the water molecules are flying off in the atmosphere. It takes more energy to bring ice water up to the boiling point than boiling hot water and boil it away. And once again, that's a hydrogen bond. So it takes a lot of energy to go from from solid to liquid and liquid to gas. So it helps stabilize water in a liquid state. So that's another important thing. So we could call it high heats of fusion and vaporization. And it's unusual for molecules like that. In other words, it takes a great deal of energy to boil water, turn it into a vapor, or to melt ice, turn it from solid to liquid. Also related to that with the hydrogen bonds. It's what we call the heat capacity of something. When you heat something, if you put a certain amount of energy into a liquid, and you'll get a certain temperature rise. And it's usually expressed in terms like so many calories. In fact, the term calorie, not the dietary calorie, that's a kilocalorie, 1,000 calories. So just think of that. If you're trying to lose some weight, when you see that bag of potato chips, multiply that number by 1,000 and it looks a little bit scary. Oh my God, this is 245,000 calories. Maybe I should just put that bag back. Okay, but at any rate, the definition of a calorie was the energy it takes to raise 1 milliliter or 1 cubic centimeter of water by 1 degree Celsius. Okay, that's the old definition of a calorie. All right, now, thing is, Most liquids, it takes a lot less than 1 calorie to raise the temperature of a gram of that liquid 1 degree Celsius. For instance, ethanol, it takes 70% as much energy to raise the temperature of a certain amount of ethanol by 1 degree Celsius. That's what we call the heat capacity of something. Water has an unusually high heat capacity. And the reason, once again, is you got all these hydrogen bonds, and you pump energy into it, and things are moving around faster and faster, but you still get this constantly changing network of hydrogen bonds, and it collectively holds the water together. So a lot of the energy you put in goes into making the hydrogen bonds form and reform and break and stuff like that, rather than actually heating the stuff up. Now, why is that important? Well, if you have a high heat capacity and you're made mostly of water, it means your body temperature is going to move up and down more slowly than if you were made of something else, like ammonia or ethanol or something like that, which has a lower heat capacity. And it's especially important for ectothermic organisms that have their body temperatures the same as the temperature of the environment. So, something heats up, the environment heats up, it takes longer for your body to heat up. That's why you see lizards and frogs and turtles and stuff like that. That's why you see turtles and snakes and lizards constantly sunning themselves in the morning on the local roads. They get run over and squashed all over the place. Okay. I try to dodge these guys, but I can't always do that. I don't want to run into a 1.5-foot long snapping turtle at 60 miles an hour. That would be very bad, both for the turtle and for my tires. But at any rate, they do that because it takes a while for them to heat up. But once they've heated up sufficiently, start going out and foraging and stuff, their temperature will decline a lot more slowly than the air temperature does. Another example of the heat capacity of water, if you don't believe me, go and jump, even if it's a hot summer day and you're sweating and stuff. Now you jump into a spring that has 50-degree water in it, right? You're not going to stay in that water for very long because you will start getting really, really cold really, really fast. Because water, you know, the old saying about water, it seems like it's cold water sucks the heat out of you. That's what it's basically doing. Your body heat is going in, shaking the hydrogen bonds in that water around, but not raising its temperature very much. So it's still 50-degree water, and meanwhile you're going hypothermic unless you get out fast. That's why, you know, people, shipwrecks and airplane crashes in the ocean, if the water is like 50 degrees or less, if they don't fish you out in a couple hours, you're dead of hypothermia. Even in fairly tropical waters, 75, 80 Fahrenheit, you can still die of hypothermia if you're in there long enough. So a high heat capacity of water helps to stabilize the organism's internal temperature. It doesn't go up and down as fast with the environment as some other liquid would be. So that's an important factor in life. The water's got one of the highest heat capacities of anything we know of. Now, the last kind of factor about water is something that's really a double-edged sword. And this is unique to water, not so much because it's polar or makes hydrogen bonds, that contributes, but the combination of that and the fact that water has a distinctly asymmetric shape. In 3 dimensions, a water molecule is going to look sort of like, almost like a Mickey Mouse. You have a much larger oxygen atom, and then you got something like this. So, Mickey Mouse, Mickey Mouse. Okay, that's what a water molecule looks like, at least in 2 dimensions, okay? The hydrogens, of course, are a fair amount smaller than the much larger oxygen. Now, when it freezes up, just because the shape of these molecules, you end up getting kind of like a 3-dimensional lattice work. And that lattice work, which we call ice, is actually less dense than the liquid water. In the liquid water, of course, these things are tumbling around, so we can get like a water molecule fitting in here for a fraction of a second, and so on. And once it's frozen in ice, that's not going to happen. You're going to get something more like this. So you have a lot of empty space in ice. And as an end result, ice is less dense. Ice is less dense than liquid water. That's about the only substance that you're going to find that is like that. Almost anything else gets more dense when it freezes, not less. So what that means is that ice floats when it freezes. Why is that important? Well, it's a double-edged sword. Let's take a look at both sides of the blade here as to why that has the significance of that aspect. Okay, the upside of that. Here we have a body of water. Okay, and you got some kind of little organisms in there. Okay, we'll put a fish in here. All right. Now, it starts getting cold outside. And pretty soon what happens is the area that's exposed to the cold air starts to freeze. You get ice crystals and they merge together, and then next thing you know, you have a layer of ice. The ice floats. Now, ice, and this is an example of high heat capacity and high heat of fusion. Ice is a terrific thermal insulator. Just ask Eskimos. Remember the Eskimos, the Inuit people that lived up in, Canada, Alaska, Siberia, and stuff like that. Before, Westerners came along, their typical things were igloos. They were ice structures made out of blocks of ice. And then they have a vent hole in there for the smoke from the fires go out. They have a fire in there. And it could be 60 below Fahrenheit outside with howling 50-mile-an-hour winds, bitterly cold outside. Inside those igloos, it could almost be shirt-sleeve weather. It'd be like 50 or 60 degrees Fahrenheit. Because ice is such a good insulator. And some people have gotten lost in, polar places and things like that, trying to save their life. What they'll sometimes do is deliberately dig a hole in the snow or the ice and settle down in there to keep from freezing to death. And people save their lives that way because ice is such a good thermal insulator. So now we have the surface of this body of water frozen. It will take a lot longer for the freeze to extend further and further on down because we've got a good insulator. And when more comes in, it still stays on the surface. It will take a lot of effort and a lot of time to freeze that whole body of water solid. So that means our little organisms inside are still in a liquid water environment. That's the good part of it. Now, if that wasn't the case, what would happen? You start getting this layer, start getting whatever kind of ice forming, it goes down to the bottom. No insulation. The stuff continues to go down the bottom, and the body of water freezes, or body of whatever liquid you're talking about, freezes from the bottom up. Not good. So that means you can protect a layer of liquid water underneath a protective layer of ice, and even when things get very cold, you can still have thriving life underneath there. That may have been a big thing about 650 to about 600 million years ago, because at that time there were 2 and possibly 3 major rounds of global ice ages. Geologic evidence shows signs of glaciers and stuff in areas we know were equatorial. They call this the snowball Earth periods. The planet may have frozen. There's a lot of debate whether there were thin, narrow bands of ice-free water, kind of like along the Antarctic coast in the extreme equatorial regions, or whether the planet froze completely from pole to pole. There's a huge debate about that, whether we froze over completely or whether we froze over almost completely, but not quite. But at any rate, think what happened to life on that. Photosynthesis is hard to photosynthesize if you're buried under hundreds of feet of ice. So, and we saw from the carbon isotope evidence, biological productivity just nosedived during these episodes. But life still survived. There were reservoirs of life, possibly microorganisms that were not photosynthesizing but relying on decaying organic matter and stuff like that, that survived those episodes that lasted in some cases for tens of millions of years of global deep freeze. And yet that did not exterminate life on this planet. And when those glaciers finally started to melt, then you had a proliferation of all kinds of organisms. and it started leading us to what we call the Cambrian period, the beginnings of modern animal life. So, had ice not stayed on the surface, or had it not been such a good insulator, life on this planet could have been exterminated 650 million years ago. Now there's speculation about the possibility of the moon of Jupiter called Europa, which seems to have an ice shell about 10 miles thick, and a possibly global ocean as much as 50, 75 miles deep underneath that. Questions are there could life possibly develop there and still be there? We don't know yet. The only way to find out is actually take a spacecraft that could drill through miles and miles of ice, and that's decades, if not a century or more into the future. But it's a potential reservoir of extraterrestrial life. Nobody really knows for sure, but it seems to have the ingredients: liquid water, minerals, things like that. So that possibly could support some kind of primitive microbial life. Anyway, that's one of the cool properties about ice. Now, the downside of this thing about ice expanding when it freezes is something you can find very easily just by holding a piece of dry ice in your hands, or spilling liquid nitrogen on your hands or something. What happens? Frostbite. What's frostbite? Well, when ice freezes and forms crystals, it expands, and as your cells start to freeze, those ice crystals expand and start poking holes in your cell membrane and start killing the cells. And then when it starts doing that to nerve cells, before they die, they send pain signals saying, something really nasty is happening to me. You better do something about this. So when you have frostbite, what's happening is you're killing the ice crystals, and the expansion of ice is actually tearing the cells apart. So very few organisms can withstand being frozen. The ones that can produce large amounts of substances that act as cryoprotectants. For instance, there's a species of frog called the wood frog you find up north, and they produce, as winter approaches, huge amounts of glycerol, which can be a cryoprotectant, prevent ice crystal formation, and allow things, when they freeze, not to tear cells apart. They will literally freeze solid in winter. You can find a frog sickle out in the northern thing. And you take that frog sickle, and then you put it and gently warm it up, and pretty soon it wakes up and starts ribbiting at you and asks you where the nearest flies are. So few organisms can withstand freezing, but they have special adaptations to prevent ice crystal formation and prevent the cellular damage. So that's the downside. If you do freeze and you don't have special protective agents, it tears your cells apart and basically kills you. Okay, so that's some of the cool properties about water. We will look at other aspects of chemistry when we come back on Monday. So you guys have a good weekend. You take care. Now.